So we're going to do a quick little rejig of schedule. I'm going to talk about theory of stack processing. Then Scott will show how to use Docker, because people are leaving at 10:30, so that they get to see that. Then we'll do the quick demo of stack processing by Harish. So yesterday we spoke about how we would go about doing time series, the three families of time series techniques, so on. If you are an end user and you are trying to implement or understand how these things were done, what you would need to know is that essentially any time series estimation methodology has four components to it. There's typically image co-registration, there's always phase unwrapping, there's the stable pixel selection, and then the final inversion itself. Doesn't typically, these four components get rearranged and probably have feedback between them in the different implementations, but these four components you will always find in any time series estimation methodology. For example, like the tutorial we did yesterday, and what we've done in the previous UNAVCO class, we can do phase unwrapping first, geocode everything, that becomes co-registration. Then you do simple pixel selection, it's coherence threshold, and then you do the time series inversion. That's what we did in class yesterday. If you were to use some package like stamps, the first thing that happens is co-registration in radar coordinates, then identification of stable pixels, then phase unwrapping, and then the final inversion. Basically, you can take any type series paper out there, and you can figure out what equivalent organization of the core processing modules look like. Well, essentially, we've already looked at the giant MintPy workflow in this case yesterday. There's a lot of interest in doing stacking in radar coordinates, because I spoke about the PS and the covariance time series methods, and I said it needed rigorous degree of co-registration. That's what drives the quality of these time series methods. ICE currently, I would say in the contrib folder, there are two stack processors. One is a top stack processor, which is for doing co-registered SLCs for Sentinel-1 for top smart data. And the other one is called Stripmap Stack. And these are for doing co-registered SLC stacks from Stripmap data from any Stripmap sensor, essentially. So I'm just going to briefly talk about the implementation, the actual flowchart of these stack processors, so that you understand what's happening. I'm going to start with the TOPS stack processor. For this, it's all documented in Harish's paper on network-based enhanced spectral diversity approach for TOPS time series analysis. So the overall workflow looks like this. If you look at the figure on the left, we have DEM and orbits. These are auxiliary external data sets Sentinel provides, and DEM is SRTM, for example, by default. You pick one reference image in your scene. Can be multiple slices. And the other images are called secondary images. For your reference image, you run RDR to Geo. This was the same process we did in TopSap. You probably saw a similar diagram for topsap.py when we were running this. So you create a pixel by pixel lat long height for each pixel of your reference SLC. Now, you can then independently run Geo to RDR with just these lat long height files for each of the secondary images and resample purely using geometry. So what you have is resampled secondary images. Note that you don't have to do the whole burst, because you know this is the first course step, so you're only doing overlaps. So this is only 10% of the data volume or 10% of the processing time. And once you have these coarsely resampled secondary images, what the code does is, instead of just looking at the co-registration between the secondary and the master, we build a SBAS network. Because a secondary image that's 2 years in time away from the master is not going to correlate very well with the master image, but it's going to correlate well with a scene that's closer in time to it. So we build this 2 nearest neighbor or 3 nearest neighbor network. So you have all these relative offsets between these. This is exactly SBAS. You have relative offsets between scenes, and then you can invert it with respect to the common master reference time. Harish has very nice simulations in the paper on what the impact of the number of neighbors you use to co-register is on the accumulation of co-registration error as the stack gets bigger and bigger. You have fixed one reference image in time, and you're building a stack. And as you go away, you will accumulate error. It is unavoidable. But you can reduce the magnitude of this accumulated error by introducing redundancy in your when you're doing the co-registration offset. So in this case, there's each SAR image is connected to 2 of its neighbors on either side, 3 of its neighbors, 4 of its neighbors, and 8 of its neighbors. For co-registration, this improves the overall accuracy. Also note, yeah, question, yeah.
So if the first image is the master of the network, the second 2 get co-registered to that one,
Yes.
and the next third gets co-registered to the second one in such a way.
Yeah, the coarse co-registration is always done with purely geometry, but any ESD or amplitude correlation is done with only the 2 neighbors.
Okay, so the spectral diversity is done with local pairs. Okay.
Because if you look at the plot on the left, the accuracy of the ESD estimate depends on the coherence. If coherence is poor, the ESD estimate for that scene is going to be poor. So if picking nearest scenes, the assumption is temporally correlation is low, and you're going to get a more reliable. And you can basically extend the same logic to range offsets as well. You take 2 scenes that are 2-3 years apart, vegetation's grown, things have changed, speckles changed, you're going to get a poorer estimate of range offset with amplitude correlation. You could extend the same analogy to that. So that's what the top stack processor does. It, for the reference scene, creates the reference geometry and uses that to run secondary images, creates the coarse overlap regions only, and then use that to do all combinations of ESD and range offsets and build a time. It's the same equation as in the SBAS. You're building the 1 minus 1 sort of network, the interferograms. You invert for range offset with respect to the reference scene for each scene individually. Any questions on that? You have more comments on that, Harish? So that's what happens for tops. There's a little bit of a difference in Stripmap. I'll talk about that in a little bit. Now the question also comes up. It's like, well, Sentinel is continuing to acquire data. How do we add new scenes? Since we rely on this connectivity thing, when a new scene comes in, essentially it's going to touch the last 2 or last 3 neighbors, and you're going to make a new estimate of the offset with respect to that. Our approach has been to freeze the stack for scenes that aren't being touched by the new scenes or no offset is being estimated. And when this new scene is being included, we actually update all the things that got touched. So that's one way of doing it. There can be other ways of doing it, but that may be one way of efficiently updating your stacks. Another efficient way of updating your stacks, especially in the context of the sequential estimator, you wait for 10 scenes to accumulate and not update the stack on every new image. It totally depends on what your requirements are. If you're doing science, I think you can afford to wait for 10 images to go. Yeah. So on the implementation side, I think currently it allows you to update. It's smart enough to figure it out. But I would say you've added 3 links and you want to change to 4 links in the middle. That is not, it's not going to handle that kind of logic. I think at present, if you make sure you use the same parameters you used to set up the initial stack, I think it's smart enough to update for top stack. Stripmap Stack, I don't believe, has an update feature. Yeah. Any questions?
Sorry, I didn't follow this co-registration procedure. You said for the Sentinel one, the TOPS procedure co-registration follow the idea using basically between the range. You follow that one, similar concept. And then for the rest of the same, for the time series analysis, so you use this, but that's incorporating the Minty time series?
You don't need the Mint. MintPy has the infrastructure for doing it for the whole image. What we are saying is you want one constant azimuth offset and one constant range offset for each scene.
Right.
So that constant is estimated using a SPAS-like approach.
Okay.
It's only one inversion.
Yeah.
So you set up the matrix one, so you have the estimates from each pair, one number for each pair, and you make the inversion to get the constant for that particular scene.
Yes. Yeah, but that's for the time series analysis, but it's not for the
This is for co-registration.
Co-registration.
This is from coarse co-registration. You estimate the constant offset in range, constant offset in azimuth. You take that constant offset and do the fine resampling, and that is your stack. In TopSAP, we were doing constant offset, constant range, and constant azimuth with respect to one scene.
Yeah.
Here, we are doing time series to estimate the constant range and constant azimuth for each scene with respect to the master.
And then for these time series, so because you have 2 sub-processing approach, one is for the Stripmap, one is for the TOPS. So
these are the same for Stripmap and TOPS. In TOPS, this step is done, the azimuth step is done using ESD.
Okay.
In Stripmap, azimuth is also done with amplitude correlation.
Okay.
So that's essentially one difference. But ionosphere introduces one more complication, which I'll talk about it on Stripmap.
And then you said that when you get new acquisitions, you can just add it to build up only for the last, like...
whatever it touched to.
All right. Okay. Thanks.
Any other questions on TOPS? So the results you saw yesterday for like the covariance stuff from Harish the stacks were all processed this way. And I think David has also built nice tools to make the output of TOPS and Stripmap look the same in stamps. There's the contrib folder, there's the Ice3 stamps that takes it sort of a common interface into stamps. I'm going to talk a little bit about the difference between the Stripmap and the TOPS stack processor. Well, TOPS currently Sentinel 1's pretty much the only sensor that's going to give you a reasonable time series. So, and it's C-band. We know ionosphere impacts are a lot smaller than at L-band. For Stripmap stacking on the workflow, I would again refer you to Haresh's paper on ionosphere time series. And this is what's available in the Stripmap Stack set of scripts. So what happens in L-band, particularly because before Sentinel-1, most of us were working with ERS and we had an ALOS and a lot of ALOS data. Ionosphere plays a much bigger impact, and how Harish spoke about how ionosphere moves pixels around in the azimuth direction due to the TEC gradient. And we sometimes have to do rubber sheeting to match the right pixels in azimuth. So in the Stripmap workflow, it's optional. You can turn it off. If you're working with X-band and C-band, you don't have to do this extra correction step, but it's available, it's implemented. Is if you turn on rubber sheeting and say you're interested in ionosphere estimation, the first thing it does is it basically produces these co-registered SLCs using geometry. Then, instead of estimating a constant range offset, constant azimuth offset as a function of time, amplitude correlation is used to generate full pixel offset time series. So this azimuth offset is you basically get an azimuth offset time series at each pixel instead of just using a constant number for a given epoch. So you get an estimate of how much on that day that pixel was distorted in azimuth. And that information is used to create the fine resampled SLCs. The pixel offsets, remember, does not involve phase unwrapping. So it's you essentially run amplitude cross correlation between the images on the same windows, and then you're able to just do SBAS on the estimated azimuth offset. Any other complications or details to add to that? So if you're doing cryosphere, you want pixel offset time series, you could just use the first part to just create pixel offset time series out of a stack of Stripmap data. So any questions? So we've tested Stripmap Stack on multiple sensors, just ALOS, Cosmo, Sentinel-1 Stripmap. It's basically the first step is sensor specific. Once you bring it into the ICE format, everything else is the same at that point. So it's just like Stripmap XML, where for the different sensor, you just change the first parts of the XML file to indicate what sensor and what are the inputs. Everything else should be the same. Any questions about the stack processing implementation and why we do it in sort of a redundant way?
In terms of the sensor, like ALOS, Sentinel, radar set, these are like a current sensor. So for these co-registration, which sensor you think provides the best co-registration, and which one relatively more difficult or challenging?
In my opinion, the absolutely best thought out sensor is TerraSAR X. Cosmo is very reliable. RadarSat-2, when you have precise orbits access, it's pretty reliable. Sentinel-1 is pretty reliable. I think the problems could be probably because we haven't explored it too much, might be if you go back a little bit to ERS data. But off late, ESA has been putting out on-demand SLCs. I've had no issues just plugging it in and generating stacks with that.
Yeah, I have a question about, specifically for reader set 2, because it contains sometimes the wide mode data, which is different from a standard mode. So do you have
that Stripmap? If it's InSAR, this is not the application for it. The application clearly says this is for Stripmap data.
Yeah, it is strip mapping, but it's extended wide mode.
So it's for a SNR probably? Or
yeah.
I don't understand what the difference would be in terms of...
I think the pulse repetition frequency might be the main cause of...
I think as long as the SLC reader correctly interprets the line spacing and the slant range spacing, there should be no problem in using this tool.
Okay, thanks.
Yeah. If you are seeing issues, it may be that the reader is not interpreting that spacing correctly. That would be my guess. I know RadarSat 2 started oversampling things by 2, and we had to make some changes at some point in time. So as long as you get the numbers right, it works.
So how many master images do we have during the stack processing?
One.
Just one. We will register all other images to this master image.
Exactly.
And I have another question. If we have a pair with very low coherence, and we can't pass the ESDS mission and fill the registration, how we will deal with this card?
So this goes back exactly to the same theory that Harish pointed out. We are relying on you're basically doing SBAS to do ESD. If you can afford to throw away a scene and have a connected network, it's okay. Go ahead and throw it out. As long as you have a connected network, you will be able to invert for an estimate. Redundancy helps improve the estimate. But if you really can't use that pair, throw it out. All right, so that's essentially what I had in mind for like stacking theory and the different kind of implementations. That's Scott. Okay, any stack processor, and you can do Talker afterwards. Yeah, we can do that. Let's do that.
All right, so couple of things. The implementation of those two papers exists in IceTool, and you can actually see it on GitHub. If I go to GitHub, IceTool, this is the public GitHub, and you guys have access to it. This is the most updated version of the ICE2 software that is out there, so you guys can explore more. In the contrib folder, there are different contributed software and processors. One of them is the stack. And the stack, we have two stack processors, TOPS stack and Stripmap stack. Piyush explained both of them, and these two folders actually has the implementation there. So, and there are two README files, README for Stripmap stack, README for TOPS stack. We tried to make it as clear as possible. I believe if somebody really wants to do a stack processing, should be able to just read through this. It's not too long, but it has enough information to get you through set up your stack processor. But anyway, I'll demo it shortly. All you need to do is, if you are installing from source, it's in the README. You need to have this path in your path environment variable for TOPS stack and for Stripmap stack. So what does it do?
Is it still true that you can only have one at a time?
Yeah, they still have conflict.
So you need to
yeah. We usually
change your path
Yeah.
with respect to which one you want to use.
Yes, that's true. So we usually are using module. For example, I know I have loaded my ICE and I have loaded my Stack Sentinel module. If I want to load Conda puts in where? You can tell them.
If you get ICE via Conda, the environment variable ICE_stack will point to will contain the stack processing scripts.
It's in the shared part, right?
It's in the shared part, yeah.
So ICE, your Conda, and then share IceTool stack. So let's say I want to process a stack of Sentinel-1 SLCs. I make an empty directory called demo for today. I go inside demo. I have nothing. Since I have already loaded the module for Stack Sentinel, I have access to the code, and now there is one main call to the stack processor, stack_sentinel.py. If you just say stack_sentinel.py-h, it shows you some help and a lot of processing parameters. If you say with -H, it shows you even examples how to run this command. By now you should be able to download the DM for your region of interest. I think Scott talked about different ways to download the DM. We have mentioned different ways. Another way would be to just use the dm.py from ICE. Just a command like this should download the DM for you, stitches the tiles, and you have a DM to use. So I don't go to the DM download anymore. You guys have already exercised that different ways. Either use Sasara or just use the gdal translate command, or use the dm.py from ICE and download the DM. You should be also able to download the Sentinel-1 SLCs, and I have already done that, so I'm not going to do it again. I have downloaded actually for the same region that you guys process for TOPS. I have downloaded 3 acquisition dates instead of 2. You can imagine that you can have 300 acquisition dates. It doesn't matter. Okay, for this demo, I have only 3. So all I needed was the SLC, the DM, I have them, and the aux file, which is in the TOPS app notebook. It's exactly the same calibration file. It's there. Go back to the TOPS app notebook. You have a path to your calibration folder. And if you have downloaded the orbits for these dates, that's fine. You can give the path to the orbit directory. If you don't have it, which I don't have it in this case, Stack Sentinel is going to download it for you. So the command that I'm going to run I have the command here. I say stack_sentinel.py -s, which is the path to the SLC. I know my SLCs are here. All my SLCs, all the zip files, even don't as Piyush mentioned, don't unpack them. And then I just give the path to the DM, which we have downloaded, and then the calibration file, the path to the calibration file. What else? The orbit. I actually don't have this path doesn't even exist. It doesn't matter. Just give a path. If you have actual orbits, give the right path. Otherwise, I didn't have this morning, so I just gave a path. and the bounding box that you want to process the data for. And that's it. That's the minimum information that the stack processor needs. Your SLCs, the DM, the bounding box, dummy path for the orbit or the actual path, and the calibration file.
Question, do we need to do anything to the DEM?
It should be the path. The path should be right.
Right. Yeah.
It's in the README. I'll mention it again. So it looks at all the SLC folder based on the bounding box that you have specified, does all the setup, and if you realize it was printing some messages like orbit was not found in that directory, so it goes online, downloads the orbit for those SLCs, and puts it in the local directory. If some dates have orbit, so it uses those orbit files. So at the end, that's it. You got a stack of SLC. No, it's not done. It only sets up the configuration parameters and creates some scripts to run. But it organizes everything for you. So the main outputs are the config folder, a lot of configuration files. It can be a lot. If you have 300 SLCs, of course, there will be more files here. The main one that you want to work with is the run files. It creates this run files directory. If you go into it, you have that. You see that there are different run files. They are ordered by the order of the. This is a serial processing. It's a combination of serial and parallel processing. Some steps need information from the previous steps, so it has to wait for the previous step. But each run file itself, for example, the first one, so you have to run this run file first, and the name is clear. Run 1, unpack SLCs, run topo for the master image. And if you look at it, it actually has, this Sentinel wrapper is just a script that knows, can read this configuration file. We will take a look at the configuration file too. So it has 3 independent comments there. It could be 300 independent comments when you have 300 images. Now we had, in this stack, we had only 3 acquisition dates, so we have 3 comments. But apparently, here we are unpacking the SLCs, just those VRT files that Piyush mentioned, extracting the burst VRT and the XML files, and running topo only for the master. If you choose to use tops up, it's fine. The only problem is you have to run topo many times for all possible pairs. But in this case, we run topo, which is very expensive processing, only once, only for the master of the stack. So that's the first step, and then just from the names are self-descriptory, I guess. Run 2 doesn't do much. It's just computing for your information, average baseline, and then extract the burst overlap, basically exactly what Piyush showed in that flow chart. For the overlap, run GO2RTR, and then pair misregistration, and then the time series of the misregistration, which is SPAS time series that we talked about yesterday, but only for the misregistration. And then GO2RTR for the full burst, because now we have all the information of the misregistration, making sure that we are working on the valid region of the whole stack, and make the interferograms and merge the burst interferogram. So all the computation is exactly same as tops up. It's burst by burst, but it's just for a stack. One comment from Piyush that he mentioned, when you download the DM from somewhere, another folder, and you move it to a different folder, you should just make sure that the path of your DM XML file is correct. You should just make sure that this path is Correct. So to do that, you don't have to do it manually. You can just say fix image XML-F-I DM. That's it, and that fixes the path for you. I think those of you who were trying to process the data here, you already faced this issue and you know about this. It's in the README also. So that was one point. The other point that I want you to know is you can, okay, before getting there, if we look at the run one, you see that there are configuration files. What are those configuration files? Let's look at one of them, which is in the config folder that the stack processor generated. It says it might have different functions. Those functions need to be, if they need to be serial, they are serial there. Function 1, function 2, there could be more. In this case, we have only two functions. Function 1 calls Sentinel-1 tops, which is the reader, and the path to the zip files of the Sentinel-1 data, the SWATs that you asked for to be processed, you can specify at the stack sentinel.py command, you can specify only SWAT 1. And then the orbit directory, the calibration directory, the bounding box, and the polarization. The default is VV. If you are working on the Antarctica, you have to specify the polarization HH. You can specify at the stack sentinel.py command. And the next function is running topo. It sets up the master and the DM and the geomaster, the geometry directory, the output directory. Similar for other configuration files. For example, if you look at the, let's say, unwrap, it has beforehand, even the interprograms are not generated yet, but the configurations are there. It will expect just running function 1, unwrap, the burst has been merged, so they should be here. It sets up all the configuration for you, so you don't need to do much. That's one point. And the other point, I think is my last point, is the stack sentinel.py has a lot of configurations. You can, we have default number of azimuth looks and range looks, but you can specify it. When you are running your stack sentinel.py command, you can specify this number of looks, this number of looks in range or in azimuth. The strength of the filter, some controls on the ESD estimation, turning on or turning off ESD. If somebody believes, okay, I don't want to do misregistration, I just want to use only geometry for co-registration, you can choose your co-registration approach to be geometry. Somewhere we have that. Yeah, there is one co-registration method option somewhere that you should look for it. Yeah, co-registration. The default is NESD, which is the paper that Pew showed. You could have set it up to be geometry. Then it doesn't do overlap. It just uses the geometry, yes.
How much faster is just geometry compared to NESD?
I don't remember. The ESD stuff is on overlaps. It shouldn't take much time. It's efficient. It's only looking at the overlap. Franco, you guys have recently used it. Did you try to with NESD or geometry, and do you, on top of your head, do you know how much faster it would be for co-registration? Or you guys, I think, always use NESD, so you didn't try geometry. Yeah. Within NESD. Yeah.
I would suspect about 10% overlap because that's the overlap fraction in a burst.
Yeah.
For ice sheets, you really don't need anything.
Yeah.
If you're doing pixel offsets, you don't need any
yeah.
ESD.
It really depends on the application. And the other interesting part, so the polarization unwrapping method, you have control on a lot of parameters. I ran it for the demo. I ran it with the minimum requirements, which was where is the SLC, where is the DM, where is the orbit, run. But you can specify the processing parameters in this command, and the configurations will be set up. If you have a large stack of 5 years SLCs, you want to run it only for specific dates, you can specify it. You can exclude dates, you can include dates. If you have installed Ice with GPU, then if you turn this on, then those specific steps that are using GPU, I think David put this part in, then it will use GPU, for example, for Topo and Geo2 RDR.
There's a question about how many of these steps could be run in parallel.
So the idea of the stack, what kind of parallel?
I mean simultaneously, I suppose.
Simultaneously, yes. Every run file can be run in parallel. So if you have 300 SLCs, your run one has 300 comments. Right now I have 3 SLCs, so I have 3 comments, right? So you can run, if you have a cluster of 300 nodes, you can run, basically submit a job for this run file to 300, and instead of, if each job takes, I don't know, 2 minutes, it should finish the whole thing in 2 minutes for this run. Yeah, so instead of 600 minutes.
So Harish, could you, for those which don't have a cluster, could you talk about the run.py, which might be useful for?
Oh, okay. I forgot about that. Thanks, David. How was it? Okay. If you have a if you don't have a cluster and you have some processors on your machine, you can actually say to use for this run file, just specify the run file and the number of processors that is going to be used for that run file. I think I took it from scratch. Yes, something like that. So there are really tools there. So I hope that's clear for you that the run files, run 1, 2, 3, blah blah, run 2 needs all the information from run 1. But run 1, whatever is in run 1, are independent from each other. So if you have a cluster, you can just submit jobs to them. So that's one way of the parallelization there. Any other?
I would like to add that they've done a terrific job of isolating the workflows. If there are people who are familiar with Dask or other job orchestrating things, we would really like your help. So please, if you can contribute, that would be very helpful to everyone.
Yes.
So, I apologize if you said this earlier, but with TOPS, you needed to use the same, they needed to all be either 1A or 1B, Sentinel 1A or 1B images, I believe?
Yeah, we can combine A and B.
In this, you can combine them?
Yeah.
Yeah, okay.
Let me see if I have this one A. My 3 SLCs here are all A, but yeah, there is no problem with that.
Okay, thanks.
As far as they are from the same track. Any other question? The last point, I hope, is the workflow. The Stack Sentinel has different workflows. The default is interprogram, but if you want only a co-register stack of SLC and then take it to your own software processing, then you just specify, say, workflow SLC. Then it doesn't generate the interprograms. It stops at the SLC co-registration. So it generates a co-register stack of SLC. That's what David has for stamps, for example. Stamps users need only a co-register stack of SLC, so we can make this with the stack processor, and then David has the pipeline within IceTool in the country folder, actually. Time series, I believe, right, David? Yes, here. So if we have stamps users, please go ahead and read this part. He has README, and you can take the ICE stack of SLC generated by the stack processor, move it to stamps, and continue from stamps. Yes, Iqbal, you had a question?
Can I ask, so you said you can, when you obtain interferogram generation, where is the parameter that says how many pairs to make?
Oh, yes, thank you. Yes, somewhere here, number of connections. And number of overlap connections. So number of connections is number of connections between each acquisition and next acquisition. I think the default is 1, but you can change it to whatever you want. And then number of overlap connections, so you might need only 2 interferograms between each connection and next connection, but you have the flexibility to have more for the misregistration estimation because it's cheaper, it's smaller, so you can control that.
So for this connection, you do not specify like the time interval as a limitation?
No, I believe not. We just make sure that the area data system for TOPS app, they had time interval, and we saw problem with that. If you force it with a specific time interval, if there is no acquisition, then your network later will be disconnected. So we prefer, we don't care really how long it takes for the next SLC to come. We would like to have an interferogram. Otherwise, your network will be disconnected.
Just to add up to the country folder there doesn't have really too much documentation. Could you also link it back to ICE2-docs, because that one has a lot of
ICE2.
So under ICE framework, all the documentation in the notebooks.
Oh, we moved it, yes. ICE2, ICE framework. It used to be inside ICE2, then it was, I think, heavy. So the tutorials from last year, the notebooks are here. For example, the Stripmap is exactly what we had last year. So it's here. You already have it online. The TOPS is there. Theory, time series from last year was giant. This year was Mintbyte, so we need to add that. The ARIA tools notebooks are not in this repo, but I believe you already have it in the ARIA tools, right? Okay. Stack to stamps manual.
DM -B -F.
Okay, yes, I see the PDF.
It needs to be integer.
Do you want me to show the ARIA tools tutorials? Or? So the ARIA tools, I usually go to the issues, but okay, so where is it, David? This one? All right, so Jupyter, so everything is here. ARIA download, extract, they are the notebooks that David talked about. Yes.
You explained the option polarization mode in the stack, and how can you add multiple polarization modes?
The polarization mode in the stack processor is fixed to V because for Sentinel, the VV polarization is the default over land, over Antarctica, over ice regions, it's H. So you can specify the polarization by specifying this option, -P, whatever polarization you want.
But basically, it's going to take the like polar. If it's dual pole, it's always going to either take the VV or the HH, right?
Yes.
And if you want the other one, you have to explicitly.
Well, I believe you can specifically say, and that will go to the config file.
If I remember correctly, I think one of you mentioned standalone, even GPU version of dense offset is available under contrib, right?
That's not part of the stack processor. It's it? Oh, yeah, you're right.
When you look at the run files, you essentially see direct calls to standalone scripts. And those standalone scripts for doing just the one step are all a part of the stack processors. They're all in the Stripmap Stack folder. So the config file calls a bunch of run files, and the run files call the bare standalone individual Python programs.
I think we should add the offset workflow.
Yeah.
I mean, we have it. Minion probably has it.
Yeah. I saw a minus offset in the workflow option.
Okay. Maybe
You
we
see
have
yeah, I see an offset option there.
Yeah, okay.
Yeah.
Thank you, Piyush. Yes. Now, actually, Minion from Caltech, he added that option. Yeah, there is a workflow offset option, so if somebody wants only dense offsets, should choose that option, and it makes the config files and run files for the offset computation. And if you have compiled with GPU, then that offset computation will be based on GPU. All right, so that's pretty much it. Since we reviewed all the docs, I think I'm going to also show you the MintPy repo, if you haven't seen it.
MintPy also is happy to work with the stack processor outputs, I believe, right?
Yes. The stack processor outputs, exactly. So this is the Git repo, InSAR Lab MintPy from University of Miami. And there should be some docs folder with the notebook from yesterday is not there, but we will put it somewhere, either in the ICE or in MintPy repo. And there are probably tutorials and small baseline app. And that small baseline app is based on outputs from stack processor. And Yunjun has a stack actually processed with the stack processor for Sentinel-1, and the data is even available. Something went wrong. Yeah, probably. But anyway, the notebook is there, so you can download it, and yeah, it's very similar to what we had before. Step by step, he explains the data set that is online is for Fernandina. But the nice thing is it's exactly based on the outputs from the stack processor. So you really should be able to run the stack processor and then copy, paste Yunjun's input file for MintPy and run your own time series if you want to work with ICE outputs. All right. Anything else? All right. Scott, do you want to do the Docker?
So during the transition,
Yes.
so I think some of us saw also Ice3 under Ice Framework GitHub. Do you have any word on 3? Like, is that on our own risk? Are we encouraged to try it out, or just stick with Ice2?
I'll let Piyush answer that.
Or Paul to answer.
Well, we may have different answers. So ICE3 is under development. If you want to be a developer, feel free to participate, but it's not going to be ready for prime time. It's not going to have nearly the features that ICE2 has for quite a while. It's the sort of the basis for what we're using for the ISAR processing. So ultimately, by the time we're launched, that package should have all the things needed to process the ISAR data, and hopefully all of the features, many of the features that are in ICE2 already. Since the team who's actually paid to do this work doesn't have a charter to support Sentinel and ALOS-2 and RADARSAT-2 and all these other constellation satellites, it's not clear that ICE3 will, by that time, unless others help, have all the ingest capabilities that ICE2 has. So it's there. It's probably going to be much more efficient in terms of the code itself, hopefully more modular, and hopefully more extensible, even than ICE2 is. But I would not say that I would. First of all, it's under a branch called warning, right? And that's there intentionally to discourage you from trying to get ICE2 functionality out of ICE3 anytime soon. Okay? Is that a fair assessment? Okay. Yeah, so as part of a research task, I'm working on, independent of the NISAR team, it's funded out of ESTO right now. Hopefully the funding will continue. We're working on a graphical user interface that would allow you to basically mix and match modules from basically from a web browser and run workflows that way. That's a challenging task, and it requires that ICE3 has a degree of infrastructure that is stable and relatively complete in order for us to go to the next level on that one. So again, that one probably won't be ready as a useful tool until around launch, and it still will not have the other aspects that ICE2 has unless people contribute those outside of the NISAR project. We're hopeful that this is a little bit of a stone soup kind of thing where we put something out there and people want to contribute to it and it becomes bigger than it is. But there's only so many people and so much money within the project to build the capabilities. And again, the user interface is research funded now, not technology research funded, not project funded. So depending on how that goes, if it looks really successful, we may convince the project to invest in actually making it more operational. But at the moment, it's just a research development.
Okay, so I created a new notebook, and it's in the share. It's called Running with Docker. It's kind of like running with scissors, a little safer though. So I guess last night the homework was to install Docker. So I didn't give you any instructions on how to, but now they're here in the notebook. So if you didn't get it installed, kind of look at the first part that's getting started. Number one is to install Docker. Get familiar with the concepts and terminology. If you're going to continue using it, that's a good thing to do. So we have some links for Windows, Mac, and Ubuntu to get it running. Linux is the easiest to get Docker running on. It's sudo apt install docker.io or sudo yum install Docker. So Red Hat and Ubuntu both have their own Docker outside of the Docker Community Edition, but they support it just as well as the Docker Community Edition, so you're good to run those on Linux. Mac and Windows, they have their own desktop application that you can run. We have a link here for getting started, testing, and kind of developing, and then what we've been running are these Jupyter Docker stacks. The Jupyter project has created a lot of these different Docker images, and they have these Docker files that build the different software into them. So we were starting with the minimal notebook, added in the libraries to the Python Conda environment, and then installed Ice and NumPy and ARIA tools and all of that. So that you define all of that into a Docker file, and then you can build build your Docker image. So along with the running with Docker, it's not here, over and share. I didn't copy it. Everybody should copy it over to their work directory.
Copy it into its own folder.
Well, so this Docker file, actually what you want to do is you don't want to copy it into your work directory, you want to download it directly. So I'd suggest everybody just come and right-click, you can right-click on this and say download. That'll download this Docker file to your local machine, because that's where we're going to be running, that's where Docker's running, and that's where you'll build this image that will run on your local machine. So you can download this Docker file there, from there. So this just defines, I am not sharing. Oh yeah, I'm not on Zoom. That's why. Tried to do it over here then. Oh, that's not going to work, is it? Does anybody else have Docker installed that has Zoom installed, one of the instructors? You come down and drive and show everybody how to do it. Yeah. Okay. I don't have Zoom on my laptop, which has Docker, and then the Zoom. But then I have Zoom on my computer. So once there was a bug that required Apple to install an update on Zoom, I determined that Zoom shouldn't go on my computer. So I just need you to run like the Docker commands, yeah, and show them what happens. Oh, okay. That's good. Yeah, okay, cool, thanks. Share, notebooks, right-click on that, and save link as. Oh, that's right, it is. I'm used to lab environment where you can right-click and say download. And once you have your Docker file on your local machine, we open back the notebook.
Announcement: people who are leaving at 10:30, make sure your luggage is in David's car. He'll be leaving at 10:30 sharp. People who are supposed to carpool to the airport with David.
So once you have the Docker file downloaded.
Quick question. So those who are leaving, in order to have all the things that we learned to download, do you have to open individual notebook and download each file? Or is there an easier, handy way to just create a zip file and download?
Yeah, so probably the easiest thing to do is to create a tar file, and then you can download the entire tar file of what you want to keep.
You don't need the data. Do it from the share folder if you want, or just do your notebooks.
Yeah, maybe we could, yeah. I guess we could zip up all the notebooks into a, I mean, I think eventually these are going to be on Git somewhere, and available. So if you think you're going to be working in the next month or two,
Just do it.
yeah. Well, I mean, so yeah, most of them show up online, so they'll be available. So if you're on the Docker,
yeah, do it in its own folder. If you do it in a folder with too many files in it, you're going to copy all of your files into the Docker context, and you're going to waste time.
So
Copy your entire local folder to the Docker. So don't do it in an empty folder.
So if you want files that are on your work directory, I would suggest opening a terminal and creating a tar file with the files that you want. You know, copy everything into one directory and then run tar. No, then you should be able to go into Jupyter. Yeah, and here and whatever. You can download individual files when you click on them, but you can't download an entire directory. So, you know, that you'll get a download for the tar file. I wouldn't do the share directory because it's full of data. Yeah. Yeah. And what's in the share directory, that's what I was saying, those notebooks are going to be online. So the value is if you've been using the notebooks and making your own notes and want to keep those, that's where you would want to tar up what's in your work directory and save it. So as Piyush was saying, if you run it in the directory, it tries to copy everything that's in the directory over to back to Docker. So it was trying to I have the Docker file in here, but it's trying to copy all of this. So I'll just make a temp Docker, and then move the Docker file in there, and then, oops, temp Docker, and then run the Docker build. So if we look at this Docker file, I'll just open it. A little easier to see over here. So this Docker file is basically, it's kind of like a make file. So what we're doing is we're starting with this Jupyter Stack minimal notebook. And they have a lot of other ones. They have ones that already have some SciPy, NumPy, Matplotlib already installed. There's like a SciPy notebook. When we were trying to start with that, we were getting conflicts between the GDAL3 and the H5Py and the Ice and the MintPy. So we had to step back to a more minimal notebook. And then we came in with Conda here and installed all the requirements that we need for Ice and MintPy, some extra Jupyter stuff, extensions. Here you can install more Python libraries, so we're installing the PyRocco and the Kite. We switch over and install some other tools. So the base image is running a Ubuntu, so you can add. There wasn't SFTP on our containers. So this, if you wanted to take this Docker file and add stuff into that container that wasn't there, you can start adding all the system libraries right here.
Scott, can I just ask, could you, in all those libraries that you're installing at the top, could you put all of those into like a requirement.txt file and just do a conda install? Would that work?
Yes, but what I would have to do is copy. There's a copy command in Docker. So right here we have the sconfig file that we were using to build Ice. So that's on my local laptop. I have to copy it over into the container, and then I can run it. So it's either, so this will fail if there's not a sconfig in this directory. It's going to get to that step and try to copy this file, and it's not going to work. So in order for this to just run anywhere, it's almost better to just put them directly into here. This is effectively your requirements.txt. So we could probably create this sconfig file locally, so where we don't have, so you don't have to copy it. You can just say run, cat, and put the actual strings in there that you want to have. But Oh yeah, I mean that conda command will work. In theory, yes. In practice, yeah.
The software that you're depending on in this Docker file, do you have a sense of whether it's GPL? I mean, I see Motif there, which I thought was a commercial widget tool.
Yeah, they're all, I mean, Ubuntu is all GPL. Like,
Okay.
You can't, they're very adamant about Ubuntu being open source. So, like these libraries here, where was it? Oh yeah, these here. These are all just Ubuntu libraries. If you're going to install it on Ubuntu, you can install it here. This conda stuff is added to the Ubuntu for the Jupyter.
So I'm new to Docker. I installed Docker. I see the whale icon on the top of my Mac.
Yeah.
And I downloaded this Docker file. Now, what do I need to do?
So the whale icon should, this little whale icon up here. Yeah.
Third one.
So you can start it, stop it, restart it. You can do updates. You can set preferences. So like under preferences, you can have it start Docker when you launch, if you always want to have Docker started.
So what do we need to do with the Docker file that we downloaded?
So once you have Docker installed and running, you can create a directory and put your Docker file in there.
Okay.
And then when you run this build command for Docker to build the image, it's going to read that Docker file in that directory, and everything else that's in that directory, it's going to copy it over, and it's going to build this context and say, we're going to build this Docker container image with all of this stuff in it.
So in that case, that UNAVCO ICE 2019, that's a Docker file.
No. So yeah, sorry. So this Docker build command, we're saying Docker build, we're going to build this new image. You notice I didn't say Docker file because it's just going to look for the Docker file in that directory and build it. So this T, this -T, it's a tag. So I'm going to call this image UNAVCO ICE 2019. So once it's finished, it's still running, but you can do like a Docker images.
Copies config ICE over that folder.
Oh yeah.
I have it on the left terminal. If you do ls, I think there's a Docker folder. I think I have a copy there. Yeah, there's a.
Well, I have it on the server. I forgot about that.
Yeah, so there's plenty of YouTube videos to get started with Docker.
All right, so I put the sconfig file over there now too. So download the Docker file and the sconfig and put it into the same directory. So yeah, when we're installing ICE, this I had to do. I'm not sure if this will be. Well, yeah, I don't know if that's a conda thing or a ICE thing or. Yeah, I figured. So yeah, we just clone the repository. We copy over our config file because we wanted it to be unique for this container. It's the same config file that if you're installing it locally on your machine, you'll use. And then MintPy and ARIA tools, again, we're copying those over. This one will fail because you'll need to download the OKIMV3, or you can comment that out if you don't want that part. And if there's other software that you want to install, any kind of git clone and build you can do here in the Docker image while you're building it.
Is there a way to get the image size before you build the Docker image?
So I think when it was first running, it was building this context. Ran out of lines. So yeah, at the beginning, it was kind of rolling through the directory and building this context, and you could see how it was getting larger and larger and larger.
Right. And
So the more stuff that you install and the more libraries you put in there, the larger that container image is going to be. But the advantage of it is, so I've built this image and I have it on my machine, and it might be 10 to 20 gigabytes. But I can launch 100 containers with that, and it's only going to take up 10 to 20 gigabytes on my disk. Because it's not actually replicating this container, it's just saying, hey, this is the container that I want to run, this is the image that I want to run this container with. So it's actually using that image and not duplicating it. So then everything new that you put into that container that's running, that's what's growing. So if you put data in there, you'll see the container size starting to grow and your volume starting to grow. But it's very efficient. Docker is efficient at using your disk space. So when it's downloading these different containers, it doesn't duplicate them. It just uses them at that point. So if you do this Docker image here, and you see all these sizes, 6, 6, 5.4. Since we were starting from the minimal notebook, and it's 2.64 gigabytes, and we built a new image, this Ice2, that's 6.38 gigabytes. Really, it's taking 2.64 from here. It didn't replicate that. So it's actually only taking up maybe 4 gigabytes on your disk. Docker df.
Yeah, because there's a df, just like a Linux df that does.
Okay. Yeah, and this is very helpful if you want to test out different versions. You could have one that works, and then install the next version, see if it works, and test it out, see if it will meet your needs, and then actually keep running it. So once that is built, it'll probably take a while, as you can see. You can do this Docker images. It'll show you what it was built, and whatever you gave it for the tag, you can name it whatever you want. It'll show up as the image name. And then to run it, you can run one of these containers locally.
I think the UNAVCO Ice2 should work. Okay. So. Open up a new window. Yeah. The idea is be as efficient. Use only what you need. So that list. As you can look at the
That includes all the ones for. Can I just combine them both?
yeah.
So IceTool
IceTool doesn't have one yet, but if you really want yeah, because I don't require that one.
So I'm just wondering. Oh, I see. Okay. Let's just get the min-fi one, and that will probably be enough.
Get the min-fi all in one go.
Get them all into one.
So once your image has been built, to run one of these containers on your local machine, it's this Docker run command. And the Jupyter Stack exposes this port 8888 by default. So what this -p, it's a -publish for Docker. So I'm saying I want to publish the container port, which is the second number of 8888. So that's kind of defined by this Docker image and container. And I want to publish it on port 8888 on my server or laptop. So you can change this first number to whatever number you want, but that second number is specific to the image. And the Jupyter Stack just picked 8888 by default. You could probably go into the Docker file and change that if you really wanted to, but once it's running in the container, it doesn't really matter what port the container says it wants to run on. You can publish any port that you want it to run on. So that's a nice feature. There's these -e, these environment variables that you can run. So I'm saying I want to enable JupyterLab because I like JupyterLab. If you don't want JupyterLab, you can leave it off. I'm going to give it a name. So I'm calling it UNAVCO Ice2. You could call it the same as the tag. But the second one, this second UNAVCO Ice2, this is the name of the Docker image. So that -t that we use, you want that to be the same as this. So whatever you use for the -t when you're building it, that's what you put here. You can name it whatever you want. It doesn't really need to be named the same. And then this is the command that gets run as the container is launched, and it's start. I'm going to start JupyterLab, and then this is this notebook password. You can set your own password. If you have to do the SHA-1. If you don't, if it's on your local machine and never on the internet, you probably don't need to set a password. You can just leave the token blank, and then when you launch your browser, it just connects to it. If you do need to set a password, you can run this from notebook.auth, import password. It'll ask for a password. If I say UNAVCO Ice, UNAVCO Ice. So this is the SHA-1 for the password called UNAVCO Ice. So you can save that SHA-1 and use it everywhere. Every time you launch this, you only have to do this once. Just make a note of that, and then you know that this SHA-1 hash is UNAVCO Ice or whatever password you want. And then you can start using it. There is no username for this one. When you launch it, it'll just say password, and you put in your password. Optionally, you can, instead of this notebook app.password, there's a notebook token, and you can just leave it blank and say, I don't want a token. Otherwise, if you, I guess people are leaving. Everybody's leaving now?
Not everybody, but
Okay.
one car, 6 participants are welcome to leave.
So if you left all of that off, you'd have to look at the logs to see what the it auto assigns a token unless you tell it no token or assign a password. So. All right. You're welcome. So I tried to run this command and got this invalid container name. They don't like slashes in the container name. So I might suggest not to use forward or backward slashes in your tag names or your container names. I think actually the convention is not even underscores. I think they tell you to use dashes. So if you go and read the Docker getting started and best practices, they'll tell you what you should name your stuff. So anyway, this is the hash ID of the container that gets launched. So if we say Docker PS. Docker PS. It didn't even run. Okay. So I ran the Docker image, and for some reason it stopped. I don't know why. It's not my computer, so I'm not going to try to make it run. But anyway, you can see that it launched this image with the same hash. The nice thing about Docker is you only have to use as much of this to uniquely identify a container. So oftentimes the 2 or the 27 is enough to identify the container. You don't have to put the whole 64-character hash into it to uniquely identify it. So that's kind of nice and smart. This isn't working, so you can do Docker logs 2. It said Jupyter Lab not found. Piyush didn't have Jupyter Lab in the UNAVCO /ICE2 image that was built, so when I'm trying to run the command, when I launch this container from the image and tell it to launch Jupyter Lab, if Jupyter Lab's not in there, it just failed and bombed out. So what we can do is change it, and we won't run Jupyter Lab, and we won't enable Jupyter Lab. Oh. Let's just see if we can do this. Get rid of the backslash. I'll show it. So I was trying to just remove the Jupyter Lab stuff, but I kept the name the same. So I either have to remove that one image that was there, the one container that I had named UNAVCO-ICE2, or you can just give it a new name, UNAVCO-ICE2 no lab. So give it a new name, it's happy to launch, and it's not happy to run either. So. All right. So is anybody else having success building? Okay. So mine failed. Our build failed because it was looking for the sconfig ice. I'll come back over here, download it. Come back and move download. Config. You just download the Docker file and then download the sconfig ice. So the nice thing about this Docker build is if you see that it's enumerating or incrementing these steps. So step 28 of 45, if it fails somewhere and then you fix the error and you hit go, it picks up from where you left off. But it still failed. Okay. Do you have more than one sconfig? There's probably a different config, yeah. We run the whole thing again? No, yeah, you just run it. So if it failed, just, yeah. Yeah. Yeah, so if it did the first 20 steps of 40 successfully and failed on 21, you fix it, you run it again, it's going to pick up at 21. So that's what I was trying to do, but I did. Yeah, there we go. Okay, so I had the wrong sconfig ice file that got copied over. It failed. I copied a different one over, ran it again. It copied it back over because it realizes it was a new file. So if you didn't change sconfig or you didn't change anything, it's not going to copy it back over. So if you put a new one in there and you run it, and you're not sure if it's a new one or not, just run your Docker build, and if it's new, it's going to copy it in and do the new one. So it's this item potency that you can keep running it, and if nothing changed, nothing changes. So this is now building Ice. It'll go through and download the ARIA and all of that tool. So hopefully once you're done building that, then the run command will... What? Oh, yeah, right. Yeah. So you can comment. That's what you need to comment out. Yeah. There's a copy command for that. Okay. Okay. He left. Yeah. I guess that's the Okada inversion. Okay. So what you've been running all week is that Docker file and that sconfig. So when I was building the Jupyter Hub and building the container image that gets launched for everyone, that's what you downloaded and are building right now. Any other? That's right. So if you look at, so if you ran it and you had a Docker, if you do a Docker images and you had one that failed, you'll notice that there's these ones that say repository none, tag none. So what happens is you're building this Docker image, it's building it inside these containers. So when it fails, it doesn't actually get rid of that container. That's how it knows that it can start from where it left off. What it does is creates a new container and keeps building. So this first one that was created 3 minutes ago with the ID 265. Basically, this 824, once I made that correction, it took that 265 and said, I'm going to start from there and keep going. But, if that next one fails and you step back, eventually you'll see a successful image was built and you'll have all these nones. So you can do a Docker system prune, and it'll get rid of these.
Any online questions on screen?
So it removes all the stop containers. It gets rid of all the network. These are called dangling images. So if you're building it and it kind of fails and it's kind of out there, not being used by anything, considered dangling. So if we run that, they're still there because it's still, I guess, yeah, the building is still being continued from that one. So and if you build a new image with the Docker file with the same tag, it'll just replace that image with the tag. So mine failed with the OKINV. You can comment it out or delete it. all right, so mine's finished building. And if we run this command, then it should work.
All right, while this is running, can I get a show of hands of how many people want to show data they processed and discuss and ask questions? 1, 2, 3. Anybody else? To show data and ask questions? The data that you have processed if you want to show results. Okay. So once this is done, I think we will start doing that around 11 o'clock. So work for everyone. We'll take a little 10-minute break after the Docker thing, and then we'll start at 11 o'clock with the data you processed and questions you have for us.
Yeah.
It's not copying down.
Yeah. Yeah. So what you would want to do is if you downloaded your notebooks as a zip, you could just, so this, for the command, that -v option, so this is, so this -v option here is mapping volumes into your Docker container. So what I'm saying with this -v $home is I want to map my home directory on my local server to home Jovian. So when you, no, the home Jovian is the one on the container. So this, like we were publishing the port, the first number was what is on your machine, and the second one is what's in the container. So I would say I want to publish 888 to the 888 in the port, and I want to map my home folder on my laptop to the home folder in the container. So because it's Jupyter Stacks, the user is called Jovian, so we have to use home Jovian. If you built your own, you could, customize it if you want, but it's a lot easier just to start from here. So I've kind of just adopt this home Jovian. Yeah, and you can change it. You could say home. You could say home/work, and then map that to home Jovian work. And you can keep replicating these. Maybe you had a /data external drive, and you want to map that to home Jovian data. You can start doing that. Any volumes you can map to any other directory. So when you're writing it out, it's not locked into the container. Mm-hmm. No, it would create a new Docker container. Yeah. So one thing that you can do is if you know that you don't have anything locked into this Docker container per se, you can run it with a -rm command. So when you stop the container, it just removes the container. And then you can run the command again, and it will launch the new container. So it would be equivalent to going to start run ice, almost. Think of it that way. You launch the application to run the software, in that sense. So this Docker container is the application that's running the software, and all the data and everything else lives on your local machine.
How long does it take to launch?
Half a second. It takes half a second to launch and a quarter of a second to fail, and then if it's running, it'll run forever. So yeah, there's something going on with this computer that it won't actually launch one.
I don't have a work folder, maybe.
Oh, yeah, that might be it. So, yeah, so nothing's running. Docker, if you do a ps-a, it'll show you all. You can see that these are, failing for some reason or another. You can do log. Yeah, you can generate that. You can use this little cell here to generate a password, and you don't have to do this once. You can keep this SHA-1 and note it and use it over and over and over again. So yeah, it's interesting. Each time you run this, you'll get a different. I guess they're doing a different salt or something, because this password, this SHA-1 here is also UNAVCO ICE. Oh yeah, I see. So that's the salt. So the salts are different on these. So then that's why the hash for the password is actually different. But yeah, you would just replace this password here with yours. I mean, you could use that one. It's UNAVCO Ice. So I mean, that's what I was saying. It's the same password that you were using. That password's UNAVCO Ice, if you're happy with that. If when I run it on my laptop, I don't even put the password in, just because you go to localhost port 8888, and only you can get to that on your laptop. Is the actual, if you do a Docker PS on the command line, you'll see if the container is actually running. Yeah, so you have to have the sconfig file from the share. I uploaded a new sconfig file. So get that sconfig file where the Docker file was, and then also comment out the OKIMV down towards the bottom. It's right after the ARIA tools.
I ran the run command.
Yeah. So if you do a Docker ps-a publish a, and then do a Docker log, C01 logs, just logs, and then give it this C01. Just I mean you can just. Oh, so this isn't finding GRLab. All right. I'll have to check that Docker file. They were getting the same. Can you put the run command back up on the screen? Oh, it's in the running with Docker notebook. The build and run a Docker image. If you just go to the share notebooks, it's in that top level directory.
No, you don't need to do anything in the Docker file. You need to edit the Docker file.
Do a sudo user mod node space dash lowercase a capital G
Okay, and start.
A capital G, and say Docker, and then your username. No, you got to put your username in there.
Yeah, delete those two lines.
Now you got to log back in. You have to be part of the Docker group. So I just added your user to the Docker group.
So completely isolated.
Yep.
All right. So, any questions? It did not run on my laptop?
It was getting the same error as him, so the Docker file might be. It worked on mine, but if it works, this is what you should be presented with when you try to go to your local host.
I used it for testing.
Yeah. Yeah. So I'll figure out what might be the issue and update that. But yeah, when you put in your password, then it'll take it to your notebook. Oh, that's good.
So feel free to take a 10-minute break. At 11 o'clock, we'll start with students. Hands up again. Who wants to present? Who wants to go first? Okay. Second? Okay. Third, fourth. Okay, that order. Sort of question, are your results in your notebook, or are you presenting from your this thing? Yeah. Can you connect to Zoom? Did you get an email from Melissa about how to connect to Zoom? Okay. I can forward it to. Oh, that looks great. That's ice sheet, right? Is that an ice sheet area? All right, so let's get started with student presentations. Let's start with Vijay. Share. You can use.
Yeah, because it's not a very long presentation.
Yeah, so your files are here.
Okay.
You can click and show whichever.
That's all right.
Ah, sorry. Forget. All right, so we have our first student presentation from Vijay. Tell us what area you're looking at. Exactly.
Right. Okay. So good morning, everyone. I'm Saurabh Vijay. Actually, in the last 5-7 years, I have been mainly using remote sensing data to study changes in high mountain Asia, Greenland, and Alaska. So I didn't have something which I can process in Greenland and so on. So a colleague of mine is studying a volcanic eruption in Alaska, which is like Mount Okmok, if I'm not wrong. So this volcano erupted in July, August 2008. So then it came across my mind. So why not I process something there? So she wrote me on Tuesday. On Wednesday I started, getting all the data available and so on. So my results, unfortunately, are not very interesting. But since I have implemented, so I'm not very proud of my results, but I can show you what I have. That's right, yeah.
Okay, yeah.
So that I can just go next, yeah. 4 and 4, yeah. And then I have this one. Okay.
Yeah, up, down.
That's right. So this is the amplitude image and phase image what we have seen. So as you can see, there's some Mount Okmok. So I have cropped Alos pulsar scenes. I have processed 2 InSAR pairs. So the first one is like the unwrapped geocoded unwrapped interferogram. You feel free to laugh. There's no problem. But I can tell you what is happening here. But it's not only spatially decorrelated, also like in time, because like 379 days. The thing is, this volcano erupted during July and August, and there's no scene available on that here. So this is FBD, Alos Pulsar, spatial baseline 4,300. But then I made a combination with FBS and FBD, so it's slightly improved. But as you can see, spatial baseline is still 7,300 meters, at temporal baseline 136 days. Then I discussed with Piyush, and Piyush introduced me the paper from Harish. And why it happened, so in 2007 or 8, the spatial baseline actually got very larger. So I think that's the reason why this is so unfortunate that I couldn't process. What I really want to share about this, so I did the entire processing on Jupyter Notebook, so it was a success. And I also made a, yeah, this is a script, right? I'm not familiar with Mac, so can you? Yeah. Open with edit. Yeah. So what I did last night, I wrote a small bash script and implemented the entire processing on my laptop. So it starts right from the data search, DM download, and we translate according to ICE and everything. You give your master and slave, and then it processes the entire scene. So you have like full user control, and it works fine. I mean, the results are not exciting, of course, but I process the same scene on Jupyter Notebook and bash scripting. So maybe in future, when I'll have a fortunate InSAR pair, I can just simply run my bash script and maybe update you on that. So that's what I have. So it takes like 20 GB of hard drive on my laptop, the entire, like all the intermediate files and the final files, and it took approximately 1.5 hours on my laptop. So my feedback, like based on what I have processed, like 2 InSAR pairs, the thing is, as you can see here, and I would like to mention that I unwrapped both with SNAFU and ICU. So it's not just one, because I wanted to try how it unwrapped and where are the discontinuities and so on. So I wanted to ask, so when we unwrap, do we have a user control that we can give something like a method is equal to SNAFU over there? I don't know if you can see. So I wrote a hypothetical line where it says stripmap app.py, do step unwrap. And can we do something in a command line that, okay, it gives like a method equals to SNAFU, and I want to mask all the areas which has less than 0.7 coherence, something like that. So this is something is very like you have a user control. Otherwise, of course, you can change which unwrapping algorithm you want to have, but you have to go to XML file and you have to put it there. So it's a kind of like, I have to figure out how I can automate that. But if I do something like here, so I just gave an example, but there are several InSAR processing things where you should have a user control, and if I just have this command line, this can be done on a bash script.
So the answer is it does exist.
Okay.
But if you try to make it print, there are about 150 parameters.
Mm-hmm.
And getting the logic right, when you said 2 of these parameters are in fact 4 or 5 of them,
Mm-hmm.
that's the hard part. Like each processing step in this modular
Mm-hmm.
has its own 4 or 5 set of parameters.
Mm-hmm.
And as you saw, there are about 20, 30 processing steps.
Yeah.
And actually, this is possible, but I have discouraged it because you don't know what other slowdown you're impacting. But that's the most tested method we have is to put it in the XML. That's one thing we've tested in a better manner than doing it in command line, because it's hard for us to track the implications of making one thing in the command line.
Yeah, that's right. Yeah, because like if I want to process an InSAR pair using both SNAFU and ICU, the naming convention also have to be right. So this is like, this is also kind of feedback, because people would like to use MCF and branch cut both. But in that case, they should know that, okay, the subsequent files are named according to which algorithm, was used. Yeah, so that's there's a thing. But like if I process the entire sequence, it's a kind of black box. But like advanced scientists probably would like to have more user control in that. So that's what like I wanted to point out. Yeah. That's it.
We agree.
Yeah.
It's a question of tracking dependency of making one change here and the other.
Yeah.
Or we had limited.
Yeah.
So baseline, stage of baseline was 7,000.
Yeah.
And the plot was plus minus 2,000. That's because the plot was fucking zero baseline and physical baseline is.
So I think Piyush, are you sure that the method I used using Python, it could be something, because we already discussed this, because 7,300 meters seems very unrealistic. So I mean the method we used probably gives you like an overestimated number. Yeah. That's what.
The timeline matches up with when the orbit got reset.
Yeah, but 4 kilometers is also like for differential side interferometry. If you do it, like it's really, you know, it's like decorrelated. Yeah.
So the question was what was the critical baseline? Yeah, right. For ALOS, if you go by the theory, it's on the order of 10 kilometers. But these are also slope surfaces on one side, so that becomes a lot. Thank you.
But Rob is going to show some exciting pictures, so don't get discouraged. Thank you very much.
Thank you. All right, Rob, you're up next.
Thanks. Okay, so I'm a recent postdoc at JPL, working with a. Thank you. Working with a team of scientists, including David, who was here. Whoops, how do you make it that one? Right, and for my postdoc work, I'll be building a InSAR time series of Tibet. So here's a Google Earth picture of Tibet. The reason this region is interesting to us is that India is colliding with Eurasia at a rate of about 35 millimeters a year. What that's doing is it's building a high altitude plateau and causing widespread deformation across the region. And so one of the big arguments in tectonics since the 70s is how is this deformation distributed across the region? Is it on faults or is it through block deformation or what? So one way that we're going about answering that is building an InSAR time series across the entire region. You can see in the bright green rectangle there is track 41 of the Sentinel collection, and that's been going on since 2014. Out of this project, we can also look at freeze-thaw cycles in the area and crustal flexure due to lake level changes. So, like I mentioned, we'll be using Sentinel-1A and B satellites. These are C-band, as we've seen this week. They have a repeat time of 12 days per satellite, and there's 2 of them, and their orbits are staggered by 6 days, 12 hours, or something like that. So we get at least 12-day repeat time across this track, and at best, 6-day repeat time, which is phenomenal. So I've been processing these data using the exact same techniques that we've been looking at this week, which should be cool. The interferograms are processed with the vanilla version of ICE using the ARIA routines. So ARIA is the standard products that we've seen that come in the NetCDF form. Those are processed on Amazon Web Services. And I've been building a time series using MintPy because the ARIA products have a way of going right into MintPy to be ingested. So here's a picture from Wikipedia or something of the Sentinel satellite. And here, clipped off at the bottom, is the network of our acquisitions and their connections to each other. So we had about 4,000 frames in total that I'll be showing in this data set, which is 500 scenes thereabout, and tons of connections. Yeah. Yeah, would that help? Better. Yeah, you can see the whole frame now. Is that the best? Okay, great. Yeah, great. Yeah, so here's my preliminary result. Again, this is using MintPy. This is showing line of sight velocity. It's an ascending track, so it's going south to north and looking down to the right. So red colors you see by this convention are going to be towards the satellite. Blue colors will be away from the satellite. You can see there's a lot of motion across the profile. Again, average line of sight velocity from -6 centimeters away from the satellite to plus 23 centimeters, millimeters, sorry, I got the units wrong, millimeters per year towards the satellite. So you can see this is the background of this image is a digital elevation model. This is the NASA DEM. I've superimposed a series of faults throughout the region. You can see there's some pretty sharp deformation corresponding with the fault locations, which is good. That's what we're looking for. This really noticeable green to red transition toward the north part of the profile, I think, and I've been told, has a lot to do with the atmospheric contrast there. So the Tibetan Plateau is about 5 kilometers elevation on average and pretty flat. And then as you go north into that green area of the DEM, you lose about 4,000 meters of elevation rapidly. So that's a pretty impressive step. But even still, you can see contrasts across the, can you see the pointer? The Altentag fault here. Here's the Kunlun fault coming through across that contrast there. And yeah, so that's an encouraging result. Next steps, we'll remove, work on removing the atmospheric component, and I think that'll make a big difference. So here's the spatial coherence. This is really good. Remember, I think you guys mentioned that coherence of about 0.7 is good and encouraging as a rule of thumb. Here the values are generally above 0.8 and even 0.9, so that's great. They decorrelate in the sand dune fields here, or you lose coherence in the sand dunes in the Tarim Basin. That's to be expected. Here's the temporal coherence for the time series. The anchor point of the time series is here, denoted by the star. And again, temporal coherence, even though we have this massive 1,500 kilometer long transect, temporal coherence is pretty good across the entire thing, again, except in the dune fields. And here's just showing all three of those maps side by side. So, any questions? Yeah, Haresh. No, so I have not masked the, right, so Haresh asked if I had masked the velocity based on coherence, and no, I have not masked the velocity based on coherence. We used a water mask and that's it. Not much. Right. Yeah. Yes. Yeah, absolutely. Yeah. Matt. Okay, so the question was, even in the places with low temporal and spatial coherence, such as the dune fields of the Tarim Basin, we still have, to our eyes, a coherent-looking signal that's showing up as the red motion towards the satellite. And why do we have that? I don't know. Did we get lucky, or does it just work out that way?
So my understanding is the temporal coherence is a measure of consistency. So all that is telling you is it's either an underestimate or an overestimate. And I think it's just because the data probably are a few cycles off that it falls in the correct color bar regime.
Yeah. Yes. Uh-huh. Right. So you're asking, since this is such a long 1,000+ kilometer track, do we expect to see ramps and other artifacts just from it being so big? I haven't looked at it in enough detail, and I'm still too new to the method to really give you a good idea. If anyone else has any ideas.
My understanding is orbits are really good. What you're seeing is probably long wavelength trends in the atmosphere, and that's the more likely culprit rather than orbit. Yeah.
Thank you. Oh yeah, I just wanted to say that working with the ICE team, the ARIA team, and the MintPy team has been really, really great. They're amazingly on top of things. They really know their stuff, and they're really happy to see you be successful with their tools that they produce. So plug for them, and yeah, hope you get the chance to work with them.
Just a question. How long did it take to process?
2 hours.
Yeah. On a desktop? Yeah.
On high-powered. So on a high-powered server, I think from start to finish, this took less than 24 hours to go downloading products to time series. What do you consider a high-powered server? I forget. The SAR machine.
Oh, SAR machine. I think that's a 32-core machine with 64 gigs RAM, I think.
Okay. Yeah. Medium.
I have a question to Harish. So for this one, because yeah, like the bottom one is like above 5K elevation, and that red area is like below 1K elevation. So which area, what type of ionosphere or stratosphere do you think affect most?
As they said, since the velocity clearly is correlated with topography, I don't think if it's mainly driven by ionosphere. I think it's mainly driven by troposphere. As we know, it's topography dependent. Topography doesn't form ionosphere. Ionosphere is really high. Troposphere is low, and it's shaped by topography. So I think it's troposphere. Well, we are looking at relative measurements. So probably some water vapor is trapped at the low elevation. I don't know about the climate of this area, but probably that's what is happening usually. I don't know if water vapor is coming from somewhere. It's high elevation. It doesn't go all the way up. It's trapped at the low elevation, and you see it more in that valley somehow. Just speculation.
Thank you. So where's your reference point for time series processing?
So I was lazy and didn't put it on the last figures, but here it is in that region. Yeah, so that was automatically selected by MintPy because it thought it had the best coherence and location. Oh, okay, so maybe it's in a permafrost area, and that's not the best. So I can experiment with manually locating that point. It's one thing to look into. Sengho, did you have a question?
Did you start from the standard products? So processing time doesn't include ARIA's processing to produce interference.
Thank you. Thank you. Francesco? CIC address?
Okay, I have a quick endorsed Jupyter notebook of the I have processed to SLC regarding the Amatrice earthquake in Italy. No particular reason, very big event, and I like felt in duty to honor the instructors. So So after dinner yesterday, I tried to do something. Actually, it's also my first full interferometric chain because I stopped usually with covariances matrix and I work on that stuff. And it was kind of exciting for me to have an unwrapped interferogram for the first time. So I just followed the TOPS chain that we have seen in the classes. And what about the data? Are two, as I told you, they regard the Amatrice earthquake, and the spatial baseline is around 40 meters, so very small, and the temporal baseline is less than 1 month. So the first acquisition is on the 27th of August 2016, and that I've used as master, and the first acquisition in time is the 28th of July, and it's the slave in our stack. So I did all the classical steps. You can see the dam and so on. Everything went fine. And I will go quickly. This is applied the SD. Maybe it can be interesting to see. Okay, these are the shifts that have been computed with the SD. The zone is very, the area of interest that I have selected for time reason, it was quite small, so you can see it's not so dense, the histogram, but the median is around very, very small acceptable azimuth shift. And then we, well, this is the shifting range that has been computed with the amplitude cross correlation that it's bigger compared to the azimuth one. And this is just showing one burst ESD. Okay, so this is the first interferogram, not filtered. Yeah, just, but you don't have the zoom with the pad here? Okay, yeah, it's working. So here there's a signal from the earthquake. It's not so clean. It's very noisy, the interferogram, but with the power spectrum filter, we can achieve better results. And this is this first interferogram is without ionospheric correction. Then I applied also the ionospheric correction, while I didn't apply the tropospheric because I wasn't in time for doing that. And here we can see we have, I didn't know anything about the geological aspect of this event, but okay, I noticed that here the fringe rate is higher and that there's a source of decorrelation here, so that is messing a bit the interferogram. But okay, the unwrapper was able to take out something that I don't know if it's, I don't know which were the actual displacement in the event, but here we can see a downlift and uplift of the Earth. The downlift is very, if you see the color bar, is more saturated on the uplift value. Sorry. So actually the downlift is much higher. It's around 35 radians. So we are talking about almost 6 cycles. The wavelength is 5.5 centimeters. So around 30 centimeters downlift. I don't know if matched what. I guess it's very strong movement. I don't know if correspond what actually happened during this earthquake. And this is the geocoded displacement map. Unwrapped interferogram. Applying the troposphere doesn't change so much. Yeah, sorry? Okay, sorry. Applying the ionosphere correction, we don't have so many difference. I'm sorry, because I processed everything sequentially, so I cannot compare the two images. There's some difference, but okay, globally, going back again to the geocoded interferogram, unwrapped interferogram. We have the same extreme scale, let's say, of the displacements. And the orbit was descending, just to say. And I don't know, I'm not able to give big insight of the event from a geological point of view. So I don't know if someone of you can help me in seeing if the displacement were correspond actually to what came out from this interferogram, or if it was completely messed up. Okay. Okay.
You interpreted the -30 on one side. If you look at the min and the max.
As total. Okay.
Because you don't know where the zero
the zero, yeah. Okay. So the total displacement is very big. Is 40 radians. Yeah. Questions?
I just wanted to say, it looks like if you go back to the interferogram, yeah, that one, and you zoom into that. This is filtered, and you can still see that there's a lot of noise. Can you zoom in even more?
Yeah, it's very noisy in the center.
Yeah, it's very noisy there, and I would guess that the unwrapper just unwrapped right through that noise and
get more
got more noise. It's probably that area is mostly noise, I guess, but I could be wrong. The scale in unwrapping can often be misleading. If you scale it in a particular way, you might see something that looks like displacement that's not actually displacement.
This is a more general question. Does anyone have an estimate for what the unwrapper will do if you feed it a random vector field? Like, what's the estimate for the unwrap phase at different distances?
Always look at connected components. Always look at connected components. You'll most likely see it'll all get labeled as 0 connected components if you give it a random vector field. Yeah. You see the part around the earthquake is largely labeled with a 0. So it's basically telling you, I've given you a solution, use it with caution. The SNAFO itself doesn't trust the solution in that area. Like, where's the laser? You see this little dark thing that's 0. Yeah. So it says, I've unwrapped it, but I don't trust it. So basically, you guys should remove anything that is so there were a couple of interesting things. You saw a range offset of 0.5 pixels. I suspect that's because we are looking at a small cropped area and the earthquake signal bias the histogram. You do a bigger area, you're reducing the impact of the earthquake, and you'll go towards the true geometric.
Yes, that was suspicious.
Thank you.
Thank you. Hello, everyone. I'm Zhen Ming I'm first year PhD student from University of Reading. And this is some data I processed recently. Yeah, I'll give a brief introduction about the permafrost. We can see what is permafrost. It's ground or rock. It remains below the 0 degree and for at least 2 consecutive years. And it's this, we can see this area. This is a typical type of permafrost. We can see the active layer. We can see the ice in the permafrost. So other warming climate, the permafrost will melt, and the active layer will sink, and we will have deformation over the surface. So this is the distribution of the permafrost all over the world. We can see this map. It's almost in the Arctic, and we can see some in the Tibet and the Mongolia plateau, and we also have in the Antarctic. So why permafrost? Recently, it changed rapidly under the warm climate. It has positive feedback on the warm climate, and the permafrost has around 2 times carbon in the atmosphere now. So it will change the landscapes. It will produce permafrost, and it will also damage the infrastructure. So this is my research region. We can see this is the North Alaska, and my research region is in the red box. This is the SWOT 3 of the Sentinel 1 in this frame, and okay, I will. So this is the interferogram generating process. Actually, I limited the temporal baseline and the spatial baseline, so I thought I will got good result because I think it will have high coherence between those pairs, but it's just theoretically. So finally I got around 87 infograms. You can see the, oh, it's not clear. You can see the dashed red lines. It's failed pairs because it failed during the ESDS mission because of the lower coherence. So I didn't get the consecutive pairs, so I can't do the long-term time series. So I just used the infograms I got from summertime of 2018. It's around the 20 in the dash in these books. It's around the 21 infograms. So this is the phase map. We can see the phase change. Someone like to give some comment about this kind of pairs. It's affected by atmosphere or it's just part of swans. Yeah. Yes. It's around 1 degree by 1 degree. Yeah. No.
Oh, this is done at Reading or something?
Yeah.
Okay.
I processed it recently. It's around a few weeks ago.
Okay, but using ICE?
ICE, yeah.
Okay, got it. Thank you.
Yeah, geocoded.
Did you process pair by pair or using the stack processor?
Yeah, this is pair by pair. Yeah. Actually, I didn't extract the amplitude image. I just keep the phase image, but I have it. We can see the. Is that a burst boundary or is that a feature? Actually, there's no such a feature. It's a little bit weird. We can see later. Because in the next one, it's not aligned. So I'm trying to understand how the burst boundary is aligned. It's also showing up a different parts of the ground. And we can see this is the coherence map of those infograms. Sometimes it's good, but sometimes you can see between the period of summer and spring, it's mainly affected by the snow, so it has lower coherence in this fridge. Okay, I also tried the atmosphere correction with GCAS, but look at this. This is the unwrapped phase I got from the ICE output, and this is the atmosphere delay from this GCAS model. And this is the phase after removing the atmosphere. So initially I thought this is maybe is atmosphere delay, but it's not. So the last one is the phase map after removing the atmosphere and removing the planar trend. And this code is supplied by the GCAS. You can download it from its website, but you need to be care about the resolution of the atmosphere delay, because they have the fixed resolution. So they thought you will input the same resolution image of the phase map. So you should be careful, or it will give the wrong output. So this is, I picked another one, just to set as example. So it looks have some effect, but the final result is a little bit tricky. So this is the cumulative deformation map I got from Giant, used the previous 21 infograms. We can see the change, but this error is the C, so that we can see it's very noisy. It's water, yeah. So I masked it later. Yeah, we can. Oh no, it's just chief. Forget this. Okay, this is the mean coherence of the all 21 interferograms. So I averaged all the coherence of each pixels. So all the average on average coherence of this average coherence map is around 0.4. So I masked the pixels whose coherence lower than 0.4. So I thought I masked some errors with lower coherence and some white bodies. So we can see this part is the cumulative deformation map. I didn't apply the atmosphere correction. This part I applied the atmosphere correction. Those two pairs we can see the change. It do change, but later. See, this is in result I extracted from around this area. It's just around 76 pixels. So I plotted its time series. This map is applied without apply atmosphere correction. This part.
Where is the reference pixel? How far is the pixel?
Very close to this area. I choose the very high coherence area as a reference pixel, but it's not very. After you apply this, use this pixel as reference point, but after you plot its time series, it also has changed. Yeah, but it also has changed. So it's yeah. So it's just I just mentioned. It's very important to find a good reference point in the Pampas region. So see these two maps. Without removing atmosphere delay and removing atmosphere delay, so we got almost the same result. Just very, very slight change you can see here and here. Okay, that's all. Thanks all the instructors.
So I have a question about your coherence maps. Can you go back to that average coherence? So and the top left, that's water, is that correct? Is that frozen water or liquid water?
It's seawater.
Okay, that's what I was assuming. I just wanted to ask because the average coherence for that is 0.4, but if it's water, it should be 0. If it's, the actual coherence is 0. So as we learned on Monday, when you have an average coherence of 0.4 in a place where it should be 0, it means that it's a very biased estimate, meaning you probably took very few looks to make this image. So do you know how much averaging was done to create the coherence estimate? That's question number one. And then question number two is, for this average coherence down the stack, did you use the coherence was computed for each interferogram and just average that, or did you recompute the coherence in time somehow?
I just averaged them.
Okay.
I didn't recompute them.
Okay.
How many looks for the processing?
It's around 21 by 4. 21 by 6.
100 looks, and you still have an average of 0.4. That seems strange. I think something might not be quite right in the processing. Exactly. Yeah. Exactly.
Can you go back to maybe go back to the plot that you showed the coherence of the individual interferograms?
Okay.
Yeah. Next one. Yeah. Can we see how much is it on the water?
Well, yeah, it's very dark on the water, on all the water.
Oh, yeah. It's easy.
Oh.
Hard to see the color scale, but
black is 0.
okay. Except for the last interferogram, that looks like completely decorrelated. Yeah, and those at the beginning. Otherwise, what do you think, Paul? I think.
Yeah, so that was, this makes more sense. Each of these makes more sense. That the average coherence in the water is lower than 0.4 in each one individually. So perhaps your averaging process for the average of all is somehow incorrect.
Yep.
Because it should be lower based on the average there. Yeah. So you just need to look at that step.
Yeah. Yeah. It's going to melt.
And also after October, it's also transition
Yeah,
period.
it's reason period.
The pairs found this year in those periods are not very stable, do not provide very stable coherence. So maybe you cannot use them for the analysis and it's not average coherence.
Yes, it's a problem.
Following Harish's tutorial, I would not use the first two. Do not use the last one.
Yeah. You're right. Actually, we want to do some time series, you know, so, but we even can't generate enough in programs. Yeah.
Only is over 24 days. It's hard to have very
Yeah, I mean, it's flat.
So the question was, how do you remove the atmospheric noise?
How to remove it? Oh. Actually, because it supplies the code and the atmosphere delay. So if you got the output from the ice, you just apply it. Yeah. Yeah. Okay.
Anybody else who wants to show results or talk about results? Are you sure you don't want to talk about your results? Because I think you're the only one in the room who is working on IceTool application.
Was there anybody online that had anything they wanted to show? Oops, no, I don't want that.
There was also a request for a Q&A session, and there was also a request for a Q&A session, and Garrett received a couple of emails. I'm gonna quickly pull it up. So here's 3 questions from one user. To share my screen. So if you have questions in mind, please bring it up now. This is a good time. You have about half an hour to ask questions of the instructors here. So first question that...
You got 3 minutes.
3 minutes. Yeah, so first question was, in Stripmap app and TOPS app, there are steps to do co-registration via geometry or intensity. Are there standalone modules? Yes. Oh, it went right. Yeah, so the question was, are there standalone modules to do these individual processing steps? The answer is yes, and that is exactly what you are using. Two URLs. So when you look in the individual stack folder processor scripts for Stripmap, you will see individual scripts for running topo, geo2RDR, dense offsets, crop frame. Essentially, the stack processor is sequentially calling these. So if you just want to run one step, look at the individual script for that one step. And most individual processing scripts are really simple. They'll say, import ICE, import this module from ICE. Here are the two inputs, load the metadata for the input, set up the input for the module, run the module. That's typically the nature of each of these individual scripts. So that was the first question. The second question, is there any documentation on which application is appropriate for various satellites? We have tried to be very explicit. We call Stripmap app and TOPS app, which means you don't want to try running ScanSAR data via Stripmap app or TOPS app. There is a ALOS 2 ScanSAR workflow under development, timeline TBD, but the mode in which a particular workflow works is captured explicitly in the app's name. The GUNW standard product will be processed globally and made open source with InSAR's data. I believe it is yes. It will be done globally. The nearest pair in time will be done globally and should be made available. At least that's the current plan for InSAR. Any other user questions online or? Oh, chat button there. How to select precise orbits for from Sentinel website for a given SLC? We process a lot of Sentinel-1 data. We don't try to go download each time. If you look at the TOPS stack folder, there is a script called deload orbits. We just run a cron job where we run it once a day, and it will just pull any new files that are on the system into a folder. We just have one folder with all the orbits in it, and we just use orbit directory, and we let the app itself search for it. Sasara also downloads the Sentinel-1 orbits if you have the file names in there. Scott showed the other day how to do it.
Yeah, I guess when we're talking about Sasara, if you're doing Sentinel-1, you can give it the --download, --dim, and --S1 orbits. And that will actually get you all the data that you need for doing the stack processing. And if you already have the data downloaded, it won't download the data again. And maybe you don't have the orbits, so if you just run it with the --S1 orbits, it'll download all the orbits. And it looks at the files that are in the directory, and it gets a precise orbit if it exists, and it gets the restituted orbit otherwise. So if you come back 21 days later and you run the same command, it will download new scenes, get the precise orbits for the old ones that you have, and then download restituted orbits. So if you want to continually do processing, you can keep running that Sasara, the same Sasara command in the same kind of raw data directory, and keep getting the new data and the new orbits as they come in.
It happens at the very first stage. So if you have to change orbits, you have to go back to the very first stage of the processing. Delete the whole folder, start all over again. Yeah.
What is the advantage, disadvantage of
inversion algorithm? I'll let Harish answer the MintPy question.
So the question is, what are the advantages and disadvantages of different inversion algorithms in MinPy? I believe we have two different kinds of inversion algorithms, either weighted least squares or unweighted least squares. I would suggest to use weighted least squares. And that's simply because each interferogram might have different coherence, which means different noise, different standard deviation of phase, and you are weighting it properly. So I would use one of the weighted least squares, and you have three different ways to choose the weight. Take a look at the paper, please, and we have evaluated which one to use. The inverse of the variance, I think, is the recommended way.
So the question here is, if you want to use the ICE modules and other data, should I bring it to ICE data format? You will need the XML file at least, because for read operations, ICE, I believe all modules delegate to GDAL. So if it's a .tiff file, you'll have to create the .xml and .vrt, but you don't have to recreate the whole raster all over again. One exception might be dense offsets, because of the old Fortran style of coding. It was kind of hard to make GDAL work with it. I think that might be the only exception I can think of from the top of my head. The question is how to bring in other format data to work with ICE modules. Mm-hmm.
It might be interesting to have an opportunity to get back together again.
Right. That's something we can bring up with the UNAVCO thing. I would strongly recommend that putting it in the feedback form that we're supposed to. I would recommend putting. Yeah, so it's probably, that's the right place to, based on last year's feedback, we had a pre-course silicon this year. Maybe we need a post-course thing too. Maybe that's something you suggest in the feedback and we incorporate into this. Yeah, there's always ICE forums or GitHub issues where you can raise questions and discuss things. Yeah, it'll probably have to be virtual, like a telecon, but that's something we can think of, yeah. Any other questions? Yeah, so there's a Python script to convert GIS to ICE or GeoTIFF to ICE. Yes, those were in the days when ICE did not have GDAL support incorporated in it. You don't really need to do those special things nowadays. GDAL directly recognizes ICE products. Is it possible to have installed both Ice3 and Giant? Giant is still stuck in Python 2. You saw all the wonderful things about MintPy. MintPy is more actively developed, better documented. I would recommend switching. There is currently nobody working on porting Giant to Python 3. So, so the answer for that would be no. So there's a MintPy question on topophase. Yeah, so the question is coherence is in topophase.core PHSIG file. If I want to use coherence in MintPy, what file should I pick? Is it related to multilooking? Is it reasonable to pick topophase.core if I use small number of looks? So like we discussed in the Stripmap app and TopSap notebooks, topophase.core represents coherence in the unfiltered wrapped interferogram. But what we unwrap is the filtered wrapped interferogram. Once you filter the data, the topophase.core estimate is not representative of the quality of your filtered interferogram, which is why we create the phase sigma.core interferogram. So it depends on what product you want to use. If you want to work with the unfiltered wrapped interferograms, use the topophase.core. If you want to use the filtered unwrapped interferograms, use phsigma.core for your.
So regarding the question about yield to ICE,
Yeah.
then do you mean that what is it, GDAL to ICE XML.py?
Yeah.
That way you can generate
XML and VRT. Yeah.
And
yeah, actually, you may also be able to do GDAL translate minus OFIs. I've never tried it, but there's pretty good interactivity between GDAL and ICE now. You don't need custom scripts once we start moving towards that framework. ICE. You can Google it. Yeah. Any other questions? Any speckle filters applied after generating amplitude images? No, we don't do. The workflows are very interferometric focused right now. We don't do anything in the speckle. The only thing we've done in the speckle domain is take output of stack processor, do the covariance like stats that we showed. So there's nothing in the ICE currently. So Francesco mentions he's implemented a speckle network. Would you? Is the paper? Is it in open source? Is the source open source? There we have to. Okay, so whenever it's ready. Easy. Okay. Okay, so good. Okay. Yeah. Yeah. Yeah, that'll be great. Maybe we can work on that when you visit. Also, a question, in my personal experience, time series in NetPy is smoother and less noisy than InSAR for Sentinel data. Is there a reason behind that? So that question you asked does not have enough information in it. What do you mean by time series? How far from the reference pixel are you looking at? Are you filtering the interferograms before MintPy? Are you, you need to provide more context to support that, or at least clarify that statement. What are you doing for your MintPy time series? Is it multi-looked, filtered, unwrapped interferograms in geocoded space? Is it in radar coordinates? Like what process? Yeah, are we using the same network for stamps and ICE and radar coordinate and MintPy? Yeah, so you have multi-looked the data, and you probably also unwrapped it, which means there's some filtering involved. You do expect less speckle in the time series. And depending on the terrain, if you're working with stamps, the reliable point density might also not be that great. So those are all factors you have to take into account when comparing those two sets of results. There's another question on ERS and NVSAT. InSAR app.py is not really used. You use Stripmap app.py for all Stripmap data. There's a whole bunch that needs to be filtered out. That's been there like from the beginning that we need to clean up. Yeah. Yeah, question?
I want to ask, when you do Stripmap with MCRS, can you still do the digital chemical frame and put it together?
Yeah, it should do it. But I would highly recommend looking into ESA's on-demand service. The quality of the SLCs are, at least I feel, are way better than the original, starting from the level 0 data. Off late, that's what at least I've been doing for stack processing. Stripmap app basically is what I would call the best processing methodology that we sort of needed to make TOPS work, and then we migrated that to TOPS app. InSAR app is still the old way of polynomials, and it also focuses to a common Doppler and things like that, so it's less conducive for a stack operation. Yeah. Any other questions? Oh, there's lunch here? Okay. Okay, so should we grab sandwiches, go outside? So logistics, we should plan to probably leave 2:15 from here. People who are going to carpool with us, just make sure you're in front of UNAVCO by 2 o'clock. The rest of us might walk across the street after lunch and hang out in the area. Yes.
So guys, on behalf of all the students, I would like to thank all the teachers, Scott, Piyush, Harish, Paul, and David, and Garrett. So we really appreciate it, and huge round of applause to you. And I would also like to mention that this week has been very exhausting and tired for all of you, but you really have done a great job with a smile and happy. Of course, you have taken a day out, a teacher's day out on Wednesday, so that you must have taken like crack jokes about us, about our silly questions. But yes, you have answered all our questions. So yes, and I would also like to mention that you have not taken for granted the online students as well. So you are always taking care of the mics and everything, that they are also following what we are doing here. So thank you very much, and yeah.
All right, I guess that concludes the short course. Thank you.